Good morning, everyone. I'm Sai Shishir from class 8H, and today I'm going to be presenting my idea, which is how drone agriculture plays a major part in modern agriculture. So, modern agriculture is an evolving approach to agriculture innovations and farming practices that help farmers increase efficiency and reduce the number of natural resources like water, land, and energy necessary to meet the world's food, fuel, and fiber needs. Drones have started playing a key role in modern agriculture through aerial mapping, plant health monitoring, weed detection, etc. etc. So, the objectives that we intend to find with these case studies and experiments are boosting yields with the analysis of drones, along with the help of drone UI and expertise, reducing fertilizer application by reducing inputs through capturing infrared images. 3. Increase the quality of yield through drone data and ensure better care and treatment of the plant. All these objectives also focus on reducing the costs, also reducing the amount of money used by the farmers for buying fertilizers, pesticides, etc. So the materials used in all three methods differ as their objectives are different. 1. EB drone multispectral sensor NDVI map nitrogen fertilizers. 2. EB drone NDVI map infrared sensor ground station software Amazon mobile test kit and a tractor with a tracking system. 3. EB drone mini propeller multispectral cameras NDVI map optical SAR and RGB camera. So EB is a fixed wing mapping drone which is used by small and large farmers for mapping their fields. So the methods for these case studies are method 1. The drone flew once or twice per season and also a week before the fertilizer application. They flew at an altitude of 150 meters and captured images using the multi-spec 4C camera. In our case of cereals, the drone measured the dry matter and nitrogen absorption at some stages. After this, an NDVI map was produced in which the results were present. 2. Method for reducing fertilizer application. Obviously, first the wheat crop was prepared for winter fertilization, then an EB drone was used to capture the near-infrared images of the field. It was an autonomous flight. Its progress was monitored via its eMotion ground station software, which tracks the progress of the drone and also gives it the map route. Going on with the method, after the flight, an NDVI map of crop health was produced. By the results, a tractor was sent out to spread the fertilizer. A mobile test kit was used here to achieve perfect uniformity in spreading and to not waste the efforts that we have put into making this NDVI map. 3. Method for increasing the quality of the yield produced. After the flight plan was designed, the drone was flown in the air above the specific vineyard. It flew 120 meters above the sea level and captured up to 10 km of terrain with its multispectral cameras. Upon landing, the images are downloaded from its memory and processed by photographic restitution software. So photographic restitution software is basically the science of photogrammetry. After several hours of internal work, the program provides a series of maps which are usually NDVI. Then manure, fertilizer, etc. are added after looking at the requirements produced by the map. Data obtained from method 1. These maps prove to have a tangible effect on farmers. These maps provide the farmer with two options. One map is a detailed version designed with the automatic application in mind for small and large farmers mainly who operate advanced precision agriculture equipment for extreme accuracy. The second map is a simplified version which is better suited to more small farmers who apply the nitrogen manually or using more labor and less equipment. With these options, any farmer should be able to maximize their yield. So data obtained from method 2. In one day, the UAV can map up to 1,000 hectares of land. The crop survey showed a strong imbalance in plant development across the field. The precise timing of fertilization was also found to be quite critical. 22 hectares were fertilized in total based on the application map. This was done at a rate of 0 to 189 kg. This meant that there was heavy imbalance. Some hectares needed only 1 or 2 kg, but some needed about 170 to 180 kg, which indicated strong imbalance. Data obtained from method 3. So basically an NDVI map has a scale of 5 colors where green shows the highest and red shows the lowest quality, depending upon the amount of chlorophyll that each plant processes. The greener, the better its performance. So photos of the plantation first showed red and orange as the main colors, but then slowly changed to green and yellow after the next flight. So findings. The farmers who have used the drone service have recorded an average yield of 10%, which is outstanding, and compared to the parcels analyzed using traditional, non-drone, and mainly manual methods. It would still be not accurate for every farmer to expect such results, as yields also depend upon many more variables like rain, soil, temperature, etc. Reducing the fertilizer application rate in areas of poorly developed crop was justified. This led to 20% less fertilizer being used. The harvest also yielded 13 to 14% protein. Now, this is quite a lot of cost cutting. Drones that portrayed the grapevines from above managed to trigger the production of the unique wine in the area. It closed the harvest with 11,000 more bottles that year. That year, the farmer also spent 30% less money on compost. So these are all our objectives ticked off. So this is an NDVI map where green shows the best quality and red the lowest. This is an EB drone. This drone measures the amount of nitrogen in plants by identifying the infrared, ragnite, and gamma rays. So this is a fully equipped drone which can be used for precision agriculture. So this is an example of drone use per growth stage. Drones can also be used quite well in different growth stages, but this one is quite important, and therefore we focused on this one mainly. Conclusion. As we have seen, drones as observers in the sky will remain important for the indefinite future. Drones help farmers optimize the use of inputs such as seeds, fertilizers, waters, and pesticides more efficiently. This also allows time for crop scouting and reduces overall cost in farm production and secures high yield and quality crops. The agriculture drone market is also expected to blow up. It might go from $1.2 billion USD industry to $4.8 billion in 2024. Drone use will become more ubiquitous on large and small scale farms in a few short years. The information gathered by drones on farms is often used to better inform agronomic decisions and is known as precision agriculture. So some other uses of drones which are not yet regulated and revised are spraying application, drone pollination, planting and seeding, drone irrigation, etc. Drones have already vastly altered the agriculture industry and will continue to grow in the coming years. While drone use is becoming more useful to small farmers, there is still a lot of time left to go before they become part of every farmer's equipment roster. Regulations around drone use need to be made and revised in many countries, and more research need to be made on their tasks such as pesticides, playing and application. There are many ways drones can be useful to farmers, but it is also important to understand the limitation and function before investing in this expensive equipment. So some of the information above was taken from the following websites. The video links are also as follows, which can be used for reference. Thank you.